Welcome to AI Paper Slop, the YouTube series for AI researchers and ML engineers where we summarize the latest in tech. And today we are jumping straight into a massive new robotics paper called tt-VLA, a hierarchical robot foundation model with world model-guided test time computation.
Yeah, it's a huge one.
It really is. And just to give you the core insight right out of the gate, basically, current robotic policies just completely fail on long, complex tasks because they're only predicting the very next immediate motor movement.
Right, they just react.
Exactly. So this paper introduces test time computation, or TTC, to physical actions. So instead of just a rigid single forward pass, the system uses a high-level policy to propose candidate subtasks.
Which is such a smart shift.
Yeah, and then a world model visually imagines the future state of those subtasks in pixel space, and a value model scores them using beam search. Once it picks the best path, a unified low-level flow matching policy executes the physical movements across entirely different robot bodies.
And, the result is just this unprecedented leap in complex, multi-stage physical tasks. It basically proves that scaling inference compute works for robotics just like it does for LLMs.
Yeah, and to really grasp why generating these pixel-perfect futures is so vital for the engineers listening, you have to look at the exact spot where current vision language action models, the standard VLAs, just hit a brick wall.
Oh, for sure. The bottleneck is massive right now.
Right, because when you ask a robot to, clean a room or cook a meal, you aren't just passing it a massive string of continuous motor commands, you are demanding a sequence of highly consequential decisions.
And that word right there, consequential, it carries the entire weight of the problem. If a standard VLA makes an error and, say, drops a cracked egg on the floor instead of into the frying pan, the physical environment is irreversibly altered.
Yeah, you can't just hit subtle as Z on a cracked egg.
Exactly.
Yeah.
Because the physical world doesn't have a reset button. No amount of high-frequency, low-level replanning in the gripper's motors is going to, uncrack that egg.
Yeah.
The cost of the failure is permanently locked in, and the whole long-horizon task is instantly ruined.
Which is why action-level search is practically useless for long horizons. You can't plan a multi-step recipe by searching at the level of move the gripper 2 millimeters to the left.
Right. It's just way too microscopic. The compute would explode.
Yeah, but then relying purely on text-based LLMs for reasoning goes too far in the other direction. An LLM might generate a flawless text recipe, but if it doesn't understand the actual physical geometry of your specific kitchen counter, the text is just completely detached from reality.
Right, which is why the authors of tt-VLA anchor all this heavy compute in the perfect middle ground, the subtask level. Subtasks like pick up the spatula or open the fridge, they're sparse enough in time that you can actually afford to spend computational resources evaluating them.
Yeah, they give you that breathing room.
Exactly.
Yeah.
Yet they are extended enough to cause meaningful, trackable changes in the environment.
It's sort of like watching a chess match. A standard open-loop VLA operates like an amateur player who grabs a knight and just shoves it forward without even looking at the rest of the board.
That's a great analogy.
Thanks, yeah. Whereas this new tt-VLA hierarchy, it operates like a grandmaster. That grandmaster simulates the next 3 possible moves in their head. They visualize the resulting board states, evaluate the defensive holes those moves create, and pick the optimal path before their hand ever even hovers over a piece.
Yeah, and building on that grandmaster analogy, the actual mechanism tt-VLA uses to simulate those moves is this highly structured proposed predict evaluate loop. It is just a beautiful application of a beam search pipeline applied to physical space.
Oh, totally. So how does that loop actually kick off?
So it initiates with the proposal model. It takes the current context, so the visual observation, the global task instruction, and the execution memory, and it generates a set of candidate subtasks.
So it's basically just laying out the raw options on the table. Things like pick up spoon, place cup, or grab milk.
Right, exactly. Once those initial options are proposed, the world model takes over. And this is where the simulation actually happens.
And this is the diffusion part, right?
Yeah, the world model is a diffusion-based architecture. It takes the current head camera image and the text of a proposed candidate subtask, and it predicts the terminal head camera image. It mathematically hallucinates exactly what the visual world will look like when that specific subtask is done.
It's literally generating the future in pixel space. That's wild. But, obviously you can't just generate images randomly. The system has to somehow know if those hallucinated images represent actual progress toward the final goal.
Yeah, and that brings in the value model. It acts as the ultimate judge. It takes the overarching global instruction, for instance, make milk tea, along with the candidate subtask and the imagined terminal image from the world model.
Okay, so it's looking at all three inputs at once.
Exactly. It processes all three simultaneously and outputs a scalar score between 0.05 and 0.95. It's effectively grading how much progress that imagined future makes toward completing the final instruction.
Let's unpack how it arrives at that specific scalar score, though. Because for the ML engineers tuning in, grading an imagined image sounds highly subjective. How does a model mathematically know what a 0.95 progress looks like purely from a predicted pixel state?
It relies on a really rigorous contrastive training approach. During training, the value model is fed positive pairs, which are images that truly represent the successful completion of a subtask toward a broader goal, and then negative pairs, which represent failure states, irrelevant actions, or like early terminations.
Okay, so it's constantly comparing good outcomes against bad ones.
Right, so the model learns a highly specific representation space, where the distance between the current state and the goal state can actually be quantified. So if the task is to make tea, an imagined image showing a gripper successfully holding a spoon gets a 0.95. But an imagined image showing an empty cup being put down too early gets slapped with a 0.50 or even lower.
And because this relies on beam search, the system doesn't just stop at looking one step ahead, right?
No, it takes the highest scoring imagined futures and expands those top B branches to a depth of D. It recursively explores this whole branching multiverse of physical actions.
That is so cool.
Yeah, and at the end of the search, the reflective model looks at the summaries of these retained paths and commits to a final subtask.
And that reflective model's role is super crucial here because it isn't restricted to just selecting one of the original proposals, is it?
No, not at all. If the beam search reveals a better hybrid path, the reflective model can synthesize a completely new subtask based on the context of the search. It basically frees the robot from the initial biases of the proposal model.
Okay, but I have to throw up a massive red flag on the compute cost here. I mean, if you are building this architecture, you know that generating diffusion-based future images for every single branch, running a value model on all of them, and expanding a recursive beam search is just computationally overwhelming.
Oh, it's a ton of compute.
Right. A physical robot cannot just freeze in place for 10 seconds with a carton of milk in its hand while its brain explores the multiverse. The latency would make fluid physical movement completely impossible.
And that latency issue is exactly why they had to solve this through a highly optimized asynchronous serving architecture. The system physically decouples the high-level test time computation reasoning from the low-level motor execution.
Decouples them how? Like they run on different clock speeds?
Basically, yeah. The high-level TTC runs entirely in the background. It takes its time, grinding through the beam search and refreshing the subtask command roughly every 1 second, and then caching that command.
Oh, okay. So while the background brain is taking a full second to think, the low-level policy is just continuously reading from that cache, driving the physical motors at a high control rate of like 30 hertz.
Exactly. So the body is fluidly moving based on the last known good command, while the brain handles the heavy compute for the next stage. The physical momentum never stutters.
That's super clever. So a slow, high-level decision just delays the next command refresh. It doesn't actually cause the robot's physical movement to jitter.
Right. However, this asynchronous design creates a brand new vulnerability. If the brain is calculating in the background while the body keeps moving and altering the environment, the brain's context might be outdated by the time it finishes thinking.
Oh, I didn't even think of that. Yeah, the world changed while it was busy doing math.
Exactly.
Yeah.
So the system requires a really robust way to remember what the body just did.
Right, because to navigate a long horizon task, the high-level policy has to maintain an execution memory that summarizes the completed stages. And if you've ever tried to manage state tracking in complex robotics tasks, you know text logs are notoriously unreliable.
They're the worst.
Yeah, like if the gripper bumps a cup and knocks it over, the text memory might rigidly record a placed cup on table, but the visual reality is just a spilled mess on the floor.
Right. And teaching a model to reconcile that conflicting information without heavy human intervention is a massive challenge in robotics. But the researchers engineered this brilliant data generation trick to force the model to trust its eyes over its logs.
Wait, how did they do that?
During the training phase, they intentionally fed the model perturbed memories.
So they deliberately lied to the model's memory banks.
Yeah, exactly. They would pass it a physical demonstration, but inject a text memory that purposely lagged behind the visual state, or even hallucinated an action that hadn't happened yet.
Wow, so by feeding it these contradictions, they train the model to actively cross-reference the text with the visual state and repair its own memory.
Yes, the model learns to look at the image, realize the text memory is hallucinating or outdated, and correct the internal record before generating the next subtask.
That is so smart. It forces the system to ground its reasoning entirely in visual evidence, bypassing the need for an impossibly large, manually annotated data set of human errors. It just learns to trust its eyes to correct its memory logs.
It really does. But even with the self-repairing memory and asynchronous execution, simulating the future for every tiny action is still a massive waste of compute.
Yeah, I mean, if you just need a robot to move a spoon 2 inches to the right, spending petaflops on a beam search is total overkill.
Which is why that inefficiency is managed by the adaptive router. Test time computation is not triggered for every single step. The router analyzes the token confidence logits coming from the proposal model.
The confidence logits, it measures how sure it is about the first choice.
Exactly. It specifically looks at the mathematical margin between the top two logits.
Ah, so if the model predicts pickup spoon with 90% confidence, and the second choice is only 5%, that incredibly wide margin means the model is absolutely certain of its next move.
Right. And in those high-confidence scenarios, the router takes the fast route. It skips the heavy TTC beam search entirely and executes the direct proposal immediately.
So the heavy compute is only deployed when that margin is narrow, meaning the model is internally uncertain and debating between two equally probable but potentially dangerous paths.
Exactly. It strictly budgets compute only for ambiguous decisions.
That makes a lot of sense. So let's transition a bit to how the physical body actually interprets these commands. Because once the high-level brain has definitively settled on a subtask, like pick up spoon, how does the hardware execute it?
Right, getting the motors to actually move.
Yeah, especially considering the authors deployed this policy across completely different physical embodiments. I mean, they used everything from manual desktop arms to wheeled humanoids. Normally, if you are building for different chassis, you have to build entirely separate models or bolt on custom output heads for every unique robot body.
But they bypassed the need for custom output heads by engineering a universal low-level policy. They started with a vision language backbone initialized from Qwen 3.52b and paired it with a mixture of Transformers Action Expert.
Okay, Qwen and an OT.
Yeah, but the core engineering breakthrough here is the creation of a unified 40-dimensional state and action space.
A unified space for all the robots.
Yes. They took every possible physical joint across their entire robot fleet, so bimanual arms with up to 8 joints each, the grippers, the waist articulation, the planar velocity for mobile bases, and they mapped all of them into a single massive 40-dimensional vector space.
But wait, here is the obvious friction point for any hardware engineer listening. A robotic arm bolted to a kitchen counter doesn't have a mobile base to drive. A basic 6-joint arm has no physical motors for the 7th and 8th joint slots in that 40D vector.
Right, and that's where the solution lies in how they utilized masked flow matching. They trained the action expert using conditional flow matching, which mathematically integrates a velocity field from pure noise to the target action distribution.
Okay, and flow matching is incredibly stable for continuous action spaces, but how does it handle the mismatched hardware bodies?
By applying a diagonal action mask matrix.
Oh, I see. So think of this diagonal mask like a physical mute button. The neural network outputs all 40 numbers every single time, but the mask zeroes out the channels for motors that don't physically exist on that specific robot.
Exactly. It prevents the loss function from punishing the model for failing to move an imaginary wheel on a stationary desk arm. The mask ensures that only the active channels for a specific physical embodiment receive gradients and get updated during training.
And then at inference time, you apply the exact same mask before evaluating the velocity field and again after integration. It elegantly treats physical embodiment as nothing more than a masking problem.
It really is a beautiful approach.
Yeah, it means you don't have to fracture the model's physical understanding into specialized heads. Moving a mobile base and moving an elbow become fundamentally the same type of data generation problem. They're just routed to different indices in a tensor. It is an incredibly clean solution.
Yeah, it simplifies the whole pipeline.
And all this theory is fantastic, but we have to look at the hard data. I mean, they trained the system on over 40,000 hours of heterogeneous real-world data and tested it on platforms like the Agibot G1 humanoid and the ARX AC1 bimanual setup.
And the tasks they tested were incredibly long, like an 8-minute clean room routine.
Yeah, but the data point that really demands attention is the tomato and egg stir-fry task, specifically because it tackles a classic robotics nightmare, the salt problem.
Oh, the salt problem perfectly illustrates why direct visual mapping fails in robotics. The bottleneck in seasoning a dish isn't the physical motor control of shaking the wrist, it's the visual feedback.
Right, because adding salt to a frying pan causes virtually zero change to the pixel state of the image. The pan of tomatoes looks identical before and after you add the salt.
Exactly. And standard VLAs get completely lost here. Because they rely so heavily on the immediate visual observation to decide the next step, they either get stuck in an infinite loop of adding salt forever because they can't see that they've already done it, or they just skip the step entirely.
But tn-VLA bypasses this visual ambiguity using that explicit self-repairing execution memory we discussed earlier. Because it reliably records the add salt subtask as completed in its high-level state, it forces the policy to move on to the next stage of the recipe, completely overriding the static, ambiguous visual evidence of the pan.
Right, it remembers the past to navigate the present. But the book organization task is really where it proves its ability to navigate the future.
Oh yeah, tell us about that one.
So they tasked the robot with sorting 4 books by height, but they initialized the test with out-of-domain starting states. The books were scattered in complex arrangements that the model had never seen in its 40,000 hours of training data.
And usually, in out-of-domain scenarios, standard direct planning policies completely collapse, right? Like dropping to a 50% accuracy rate, which is effectively random guessing in this context.
Exactly. They cannot execute the task because they haven't memorized the specific sequence required for that unique starting state. But when test-time computation is engaged, the accuracy rockets to 74%.
Because the robot proposes a book swap, uses the world model to hallucinate the outcome of that swap, and the value model confirms that the hallucinated image looks closer to a sorted stack.
Yes. It physically evaluates the geometry of its decision before its motors ever fire. It isn't relying on memorized training patterns, it is reasoning about physics on the fly.
Which leads directly to the most significant finding in the whole paper, the compute versus accuracy curve. By plotting task performance against petaflops of test-time compute, the authors demonstrated a clear saturation curve.
Yeah, the data on that curve is undeniable.
As they allocated more compute at inference, increasing the beam width and depth of the search, the accuracy of the robot's decisions climbed sharply before eventually plateauing.
It is the compute scaling law, finally playing out in physical robotics. We've seen scaling inference compute revolutionize LLM reasoning. Models like OpenAI's O1 prove that giving a system more time to think drastically improves its logic.
And this paper provides hard empirical proof that scaling inference compute works exactly the same way for physical actions, provided you use visual world models to bridge the gap between text reasoning and physical space.
Exactly. Brute-forcing physical reasoning at test time is now a proven substitute for lacking highly specific in-domain training data. You can substitute vast amounts of specialized data collection with heavy compute at the exact moment of execution.
Which leaves you with a massive implication to think about. If scaling inference time compute is the next dominant frontier, what happens to robotic capabilities when edge hardware inevitably accelerates?
It's going to be wild.
Right. Picture a scenario 5 years from now. A rescue robot standing in the rubble of a collapsed building, or a surgical robot hovering over an operating table. With faster edge chips, that robot won't just react to its sensors. It will be capable of simulating tens of thousands of highly detailed, cascading physical futures in milliseconds before committing to a single micro-movement.
It alters the entire equation for robotic autonomy. The machine can foresee the cascading physical consequences of every micro-decision before they happen, drastically reducing the risk of irreversible physical errors in high-stakes environments.
A future where robots daydream perfectly before they act. They won't just move pieces on the board, they'll simulate the entire game in their heads before they even touch the first piece. We highly recommend grabbing the paper to look at the exact scaling numbers on that compute curve. Until next time, keep digging into the data.